So let me start with illustrating what kind of problem we are dealing with. So suppose this is inside an MRI scanner, okay, and this is a monitor, projector, the stimulus the subject is seeing, and this is the subject. And let's suppose this is brain activity, fMRI signals from this person's visual cortex. So our task is to tell what kind of image this person is looking at just by analyzing this signal. Okay. So more specifically, given this MRI signal, whether we can tell which of these orientations the person is seeing. Okay. Can anyone tell from this image? Maybe it's very difficult. Okay. Let me give you some clue. These are images measured during the person is seeing this left-tilted orientation, and this is from right-tilted orientation. I think even though you know where the visual cortex is, it's pretty difficult to distinguish these images. But it's, from our study, it turned out it's possible to distinguish these images. So our approach was to let the computer or machine learning algorithms to learn the pattern. Okay, and this is let's assume this is some behavior or mental state parameter, and this is brain activity signals. So we collect many data, many neural data and corresponding behavior and experimental data, and try to find the mapping between these using machine learning methods. So our approach is pretty much data-driven approach. And we applied this idea first to study, to decode visual orientation from human fMRI. So this is a stimulus, and this is brain activity measured by fMRI. And this part is a decoder, which is a machine learning algorithm, which was trained on a large data set of stimulus and behavior, stimulus and fMRI activity patterns. And then now this decoder is analyzing new data. And these are the results of outputs of the decoder for different orientations. For instance, this shows the histogram of the output of the decoder when the stimulus was horizontal. The blue line shows the distribution, and the correct answer is shown by this red curve. So as you can see, this decoder can make a very accurate prediction about the orientation the person is seeing. Okay. So you may wonder why this is possible, given that the standard fMRI signals are have very low spatial resolution. Okay. Here I'm showing a color map of orientation columns estimated from animal studies, and this 3x3 grid shows approximate size of fMRI voxels, standard fMRI voxels, which is about 3 millimeter. So as you can see, it's totally undersampling. You can never visualize the orientation columns using this coarse sampling by fMRI voxels. However, this does not necessarily mean the lack of information. If you look at, for instance, if you focus on this column and plot the histogram of areas for each orientation, you find some, bias. So you don't see, you don't see complete averaged out signals, but there are some biases for each voxels. So some voxel prefers some horizontal orientation, and others prefer vertical orientation. So even though each voxel contains very little information, by combining these small small amount of information which could arise from small biases in a columnar structure, I thought it may be possible to extract information about the orientation the person is seeing. And this is a little bit inside the decoder. And this is the input to the decoder voxels. We use about 200 to 300 voxels from primary and secondary visual cortex of the human. And this shows orientation responses of randomly picked 2 voxels. So as you can see, both voxels show very poor orientation selectivity. However, just by going through simple linear transformation, which combines information from many voxels, we can create artificial orientation detectors, which shows very highly tuned, highly peaked activity. Okay. So using this, we can make an accurate prediction about orientation. And here I'm showing a simple 1D simulation of column and voxels to give us proof of concept for the idea that orientation information can be obtained from subvoxel structure information. So here we have a completely regular column array, and this is slightly irregular columnar array, and these were sampled by large voxels. Okay, and using this voxel information, we try to decode. And here, the vertical orientation is assumed to be the correct orientation. And as you can see, if the columnar array is completely regular, you cannot decode the orientation. But just by having a small irregularity, we can readily extract information about orientation. We can make a very accurate prediction about the orientation. So this simple simulation demonstrates the feasibility of the idea that we can extract subvoxel information via some random biases of the subvoxel structures. So this is still very hypothetical, and there are group of people who are against this idea, but there's a couple of groups who are now working on this issue and using high-resolution MRI and electrophysiological recording and showing some support for our original hypothesis. Okay. So our method was basically using some training data. We train a decoder and then test the generalization of the decoder to new stimulus. Okay. So in the step of generalization, we can add some twist to perform some very primitive form of mind reading. Okay. So we first trained the decoder using stimulus-induced brain activity, as before, and then this can be used to decode brain activity pattern which were obtained while subject having some mentation about that stimulus. Okay, just imagining or just paying attention to the stimulus. So if stimulus-induced perception and subjective mentation share some neural representation, maybe we can decode